Hi folks, Emily here. My name is Emily Weber. I'm a machine learning specialist, solutions architect at Amazon Web Services, and today we are going to learn about reinforcement learning with human feedback. So this is a super cool topic in AI/ML and in generative AI. And I believe that reinforcement learning with human feedback is probably the single best way to get a really good large language model and a really good generative AI model writ large. So let's get started. All right, so first we'll come to find out that not all human feedback is the same. So this is one of the core reasons why generative AI has been a super hard task for many years. Quite a few of us, including myself, have spent years trying to generate stories, generate music, generate all sorts of things. And at its heart, the hardest part about generative AI is evaluating the context and evaluating the quality of the result. And so reinforcement learning with human feedback, or RLHF, is one really promising way to do this. However, it's not the only one. There are many kinds of reward modeling. And so we'll look at different ways of building reward models. And we'll talk through implementation options on AWS. So I have a couple options for you of ways that you can build and design your own reward modeling systems on AWS so that you can build your own foundation models and create the breakthrough apps of the future. So, and then we'll close out with the hands-on walkthrough of RLHF on AWS. So let's do it. All right, so the first concept that we want to really understand here is that not all human feedback is the same. Specifically, there are really two very different kinds of human feedback. One type of human feedback is objective. This is when humans say like, yes, obviously 1 + 1 is 2. Or if you say like the literal translation or the literal classification of something is very objective. If you look at external outcomes of some experiment or external outcomes of some action, like physics, it's very objective, it's very obvious, it's very empirical. So, for example, this square is obviously black, and this square is obviously white, right? There are two ends of the spectrum here. They're not the same, they are different. That is sort of objective human feedback. Not all human feedback is like this. Some type of human feedback is more subjective, which is to say not every human feels the same way about it. That's sort of the difference. That like with objective human feedback, if you have maybe 10, 20, 30, or all humans who look at something, everyone can agree that like, yes, this is true. That's objective human feedback. Subjective human feedback is where it's much more according to individuals' interpretations, where people have these nuanced preferences. They just like something, not for any particular reason, but that's just because that's how they feel about something. They have a gut reaction. They respond to content differently. We all interpret artwork differently. And so it's sort of like a gray scale, right? There's a large spectrum of colors. There's a large spectrum of human responses. And so our challenge in generative AI is incorporating not just objective human feedback, but this subjective human feedback. And here's why. Objective human feedback, like classification, like empirical sort of studies, empirical results from your data set, that's great for traditional ML tasks. That's perfect for, again, classification, regression, for recommendations, for forecasting. Is perfect for things like this, where you take your data and then you use that to train your model and you're done. In generative AI, it's different because the models, again, are generating not just not just tasks or not just entities, but they're generating artwork, really. They're generating images, all of these different types of images, and they're generating language, and not just sort of obvious or clear or empirical answers to questions, but many times it's subjective. And so what we want is a way to aggregate this subjective human feedback at scale. That's what reward modeling is really, really good at. So for example, in a traditional ML task, we'll take our text, right? Which is, I'm not into this house, it's too expensive, too far from the train line. We send that to a model, and then the model looks at the labels in the data set, right? Where the labels that humans could provide were 1 of 5, right? Or in this case, 1 of 2. It's either positive or it's negative. It's not both. It's not somewhere in between. It's either positive or negative. So that type of objective human feedback is useful to train a classification model. However, a generative model is going to give you something more like this, where we say, is the person going to buy the house? And then the agent sort of hypothesizes, like, it's unlikely. It's very unlikely. But what we want is a way to say, like, for the people to say, like, is this a good response or is this not a good response? So in any case, generative ML tasks need subjective human responses aggregated at scale. So we'll take an LLM, we'll have the LLM generate tons of responses to different questions, and then your human labelers actually rank those. They're going to put those into categories. They'll label them favorite to least favorite, and then we're going to use that to train a new model. We'll use that to train a reward model, which is called reward modeling. All right, so reward modeling aggregates human feedback at scale. Again, specifically subjective human feedback is where it's really perfect for this. So we'll pick a base foundation model, any foundation model. Pick a base LLM, base diffusion model, base CLIP, base llama, base falcon, whatever you want. Pick your base foundation model. And then we're going to bring prompts to that foundation model. So we'll bring your prompt data set with all of the questions, all of the content that you're really interested in for your use cases. For each prompt, we'll send that to your base model and get multiple responses. So for each prompt, you want like 4 or 5 answers. So then you have this one-to-many data set of prompts and responses from this model. Then we're going to hire human labelers to rank the responses. So you'll use like SageMaker Ground Truth, for example, to basically ask the humans to label these responses. So from the one prompt, they can then rank their responses. So they can say like, oh yes, this one's my favorite, this one's my least favorite, and these 2 are in the middle. Once you have this data set, again, with one prompt and multiple responses, and the preferences for those, we'll train a reward model. So we'll actually train a new generative model that uses those responses, but instead of just outputting a text, it's going to output a number. So the reward model outputs literally a scalar, just a number, instead of generating like text or generating images. And the reason, so it's like a regressive model. So we train this regressive reward model. We're going to use that to train a new generative model. So now we're actually going to fine tune a LLM or a vision-based generative model using this reward model that we just built. So we're going to use the reward model to fine-tune our new LLM, fine-tune our new generative model, and then we'll evaluate this thing to see how it performs and start the whole thing over again. So let's learn how to do this. All right, so again, reinforcement learning with human feedback is one of the most common ways to perform reward modeling. So what is this? So literally, just as we described, you're going to start with a data set of prompts, and then you have multiple responses. So multiple responses per prompt. You're going to send this whole corpus to humans for ranking. The humans review this, and you're probably asking like, oh, well, why will they pick certain things? Like some of them will like things differently. Some of them will prefer really short ones. Some of them will prefer really long ones. Some of them will prefer the silly ones. So you can determine some of that in the instructions for the humans, saying, please pick something that's more clear or something that's less harmful. Or you can actually say like, please search online and do fact checking for this to ensure that it's accurate. So in your instructions, you have ways of kind of indicating to the humans what you prefer. So in any case, your humans rank these. Then you're going to train a reward model using those rankings, right? So you'll train this reward model on the human rankings, and then the reinforcement learning comes in at the second piece, actually, where we're going to use reinforcement learning to connect the reward model to the new generative model. And then the reason for this is that your final model should be 2 to 3 times better than the original. So the quality of this model is so much higher than it would have been previously. It's so much more preferred by humans than it would have been without. So let's do a quick recap of reinforcement learning, just to refresh this. And for those of you who are new, this is to help you understand what reinforcement learning is all about. So reinforcement learning is a type of machine learning that's commonly used to sort of train robotic agents. So you'll use reinforcement learning to take this agent. And an agent is an autonomous entity that we're trying to train. A policy is sort of like the brain of the agent. The policy is how the agent learns. So like if we were training a literal robot, the robot would be the agent, and then the robot uses the policy, which is like their neural network, just like Arnold Schwarzenegger. When he promised us he'd be back. And so we use the policy. Yes, we have our reinforcement learning agent policy. And then the policy is going to learn how to pick actions. So it searches like in what we call the action space. So it searches in the space of all possible agent actions. It's going to take an action. And so the policy picks the action, and then the agent takes the action. And then the action produces some result. And so the result in RL, the result is produced by the environment. So you define sort of this environment that the agent is operating inside of. And so the action produces this result. Then your job as the designer of the system is to figure out what type of reward signal to provide to this agent. And so your action produces a result. Then you build this reward signal or this reward function that tells the agent, does the agent get a lot of reward from this function or a little reward? So it's common in like video games, for example. You can train an agent to solve the game, to just play the game, in which case the reward signal is like literally the number of points that the agent can get. Or if you're training a physical robot, you might use a reward signal that is like, did the robot pick up the computer, or did the robot grasp the widget, in which case that's the reward signal. So you as the data scientist here get to build the reward signal and sort of set up this whole stack. So that's a quick recap of reinforcement learning. Now let's learn how we're going to apply reinforcement learning to updating our LLM. So remember, in this case, we're going to use RL to not to pre-train, although I am a little bit skeptical about this because I think that's probably the way to go. But in any case, right now we're going to use reinforcement learning to fine-tune an LLM. And so the policy of the agent is the LLM, right? So that this new large language model that we're trying to fine-tune is the policy, and it's orchestrated by, for example, one reinforcement learning algorithm that's called proxy policy optimization, so PPO. And then the action space here is all possible tokens in the vocabulary. So for the LLM, it's like all possible words that this LLM could be generating. So that's the action space. And then the reward model is that model that we just trained. So that model that we trained ahead of time on the human ranking data sets that takes in new text and uses the response from humans to say how good that is empirically. So translating a subjective problem to an empirical problem, which is super cool. So we'll use the reward model to do this. And then it's been found that it's actually helpful to have a distance function to keep the original LLM and the one that we're training much closer. If we didn't use this distance function, then the reward model and the PPO would go crazy. like basically the PPO would be able to just hack the reward model, and it wouldn't abstract, it wouldn't learn anything, it would just be optimizing for reward. And so this way, when you add this divergence penalty function, that keeps the model generating content that's much more in line with the original LLM. Great, so a reward model, this divergence function, and then a reward function. And so the reward function combines basically that divergence term with the output of this reward model, and it's going to combine both of these two to update the agent and specifically to update the policy or the neural network or the PPO of the agent. So let's take a closer look. So mathematically speaking, let's see if we can break this down here. All right, so let's call X just the prompts from your training data set. Simple enough. X here is just the prompts that are coming in from your training data set. Maybe you're just using one from open source. Maybe you're bringing your own. I'm going to throw two Y's at you. So this Y star, so Y star is the text that's generated by the LLM or the PPO that we are training using the prompts. So I take X, which is my training prompts. I send X into the LLM that I am training, and I get this Y star. So Y star is going to change every time I update my LLM because I take my prompts. My prompts are like my mini batch. I throw my mini batch through my neural network, I run the forward pass, I get Y star at the end of every batch. So that's Y star. I'm going to call Y0 text that was generated from that original LLM, also using the prompts. So let's say, so I take the same X data set, and then I take X and I throw that into my original LLM. So this first GPT that I'm using. And I run this X through my first GPT, and I'm going to get this thing I call Y0. So again, both Y star and Y0 are like responses to the prompts. The difference is that Y star changes every time because it's from the LLM that I'm fine-tuning per batch and per step, while Y0 is constant because Y0 is from my original training data set. Actually, no, Y0 is from my original LLM. So Y0 doesn't change, and Y star changes constantly. All right, so now we got those. Let's break this down. So we're gonna compute this R theta using this reward model. So remember, the reward model is the result of this training process that we just did, where I take my data set, I have my humans rank my data set, and then I train a model that takes text and gives me a scalar. So that's this R0. It's just what comes out of the reward model. Think regressive LLM. And to my regressive LLM, I'm going to send in both the prompt and this Y star, and this response from my LLM. And that is basically telling me what humans prefer. That's this R theta, is like, how much did humans like this thing? That's what this means. Then I'm going to compute another term here. And so the second term is the KL divergence. I'm going to say Kuiper-Leibler or something like this. My apologies for getting the names poorly. But it's the KL divergence that basically looks at two distributions and computes the difference between them. And so this divergence term is looking at Y star. So it's looking at, again, both of the responses. The response generated by the LLM I'm training and the response generated from my original LLM. And so it's looking at how far apart those two things are. And so I get this R sub KD, this divergence. And again, this prevents like out of character RL hacking. So this is stopping that PPO from just going crazy. And it's ensuring that the quality of the generated text is much more in line with my LLM. So I'm going to take these two things and I'm just going to put them together, basically. So the reward signal for the PPO, which is basically the loss that I use to update the LLM, is just equal to the combination of these. So it's the overall reward that I get from humans by telling me how good this content is, minus the penalty term for this divergence, times some epsilon for however much we want to weight this thing. And then the original authors found that it was useful to add some pre-training gradients here. And this is why I still believe that once you've built this, there's no reason to not just throw this into the pre-training. I don't know why you would ever want to just do this in fine-tuning, so TBD on that. But in any case, RLHF appears to be quite promising. So this is from the Ouyang et al. Work in 2022 in the Instruct GPT paper, where they showed that PPO is really good. RLHF is really powerful. So this is your base GPT-3, and then they're comparing it with prompted GPT-3. So remember that few shot prompting we learned about with the instructions. So compared with prompting GPT, and then they're looking at this human win rate. So basically, how much do people like the response of this model relative to the responses of other models? And so, so prompted GPT is clearly better than base GPT. And then this green line here is supervised fine-tuning, SFT. So supervised fine-tuning mostly refers to instruction fine-tuning in this work, where they, again, take the prompts like, tell me about a time you had fun at the zoo, or what's the number in my bank account, or when is Father's Day in 2023 or something like this. So you tag those instructions and then you run fine-tuning. So that's supervised fine-tuning. So GPT base, GPT prompted, supervised fine-tuning, and then this one up here is PPO, and PPO stands for the reinforcement learning with human feedback. And then this PPO, this is like a special juiced version of this. So that was even better. And so your net here is that RLHF gives you a lot of boost. It's 2 to 3 times better than base GPT, and it's much better than just supervised fine-tuning, and it's certainly much better than prompting. So reinforcement learning with human feedback is shown to be a critical and extremely useful way to improve the performance of your generative AI models. Another concept, this one is coming from Anthropic on 2022, is this concept of constitutional AI, where they suggest using AIs to evaluate the AI. So certainly this makes it easier for the humans, but it's also because models are really good these days. LLMs are great. They're really strong. They're powerful. They're knowledgeable. They're excellent. And so there's this concept, like, why don't I just use AI to evaluate my AI? And so that's what constitutional AI is exploring. They train a variety of models and then essentially use the AI models to evaluate and critique the responses of these models. They also propose what's called a red-teamed dataset. The dataset is available on Hugging Face. The red-teamed dataset is full of every stereotype and every aggressive, harmful, toxic thing you have ever seen or heard or dreamed of. So approach with caution, but it's a useful data set because it helps mitigate the behavior of that in your model. So I like this approach of using AI to evaluate AIs, particularly because I myself find the red teaming data set extremely triggering. It's so triggering and it's so toxic that I can barely even load it into a pandas data frame before I need to go leave my computer and clear my head because it's so triggering. And so I like this approach of using AI to evaluate your AIs because not only is it easier and more cost effective, it also saves people from this extremely triggering content, which they can then just avoid. So that's great. So this is an interesting approach. So again, what do you need to train a reward model? So to train your own reward model, net here, you want a one-to-many data set with prompts and responses. Remember, you've got your prompt library. You've got this text file, this CSV file. Maybe you've got a Dynamo table if you're going crazy with all of your prompts. So you've got a prompt data set. And then each prompt has multiple responses. So for each prompt, you might have 5, 10, just for that, maybe 5. Maybe just 5 prompts, but you have multiple responses for each prompt, so one-to-many. And then you need a GPT-based model that's going to return a scalar. So it returns a number. So it's still a generative pre-trained transformer, but it's not generating text. It's returning a number. So I call that a regressive large language model, right? Because it's a regressive model in the sense that it's producing this continuous scalar output, but it is still a large language model at the base. Fortunately, you don't need a massively large reward model. You can get away with a 6 billion parameter model, which appears to be good enough. And so you need this model, and I'm happy to say I have some PyTorch code to share with you that you can copy and paste to get this and to run this in your own project. So you need a GPT-based PyTorch model that returns a scalar. And then, lo and behold, you need some distributed training systems to train this entire process for you. So let's break it down. All right, so again, let's try and really understand these data sets for reward modeling. So let's say I give you a prompt, and the prompt is like, what's the weather like in Washington, D.C. for something kind of casual and fun. And I live in Washington, D.C., so I grapple with these weather questions constantly. So what's the weather like in Washington, D.C.? So you got maybe 3 responses that your LLM comes up with. Maybe one is the local weather in D.C. is sunny and humid, at a temperature of 82 degrees Fahrenheit. So that's one response. Another response is, it's freaking hot. And then another response is, well, relative to Phoenix, Arizona, Washington, D.C. is a cool 82 degrees. So can you see how preferences to these change per person? Like some people and some circumstances prefer different ones. I love the second one. Like, I find it hilarious. I find it entertaining. I find it honest. However, if I were building a software application for someone who's not me, I might pick number 2 as my preference. Or if I were building an application for Phoenix, Arizona consumers and who just wanted to ask questions about life relative to Phoenix, then I might go with this 3rd ranking. So in any case, rankings vary. But in your data labeling solution, you want to give your human labelers clear instructions for what their labeling criteria should be. And then you want to give them a way to easily say, okay, I prefer this, and then that, and then that. And so you provide these rankings for the different responses. And then again, you can use humans, you can use AIs, you can create really any kind of digital signal to create these rankings. You want some preference number to rank all of these possible responses. So your data set has multiple prompts, and then you take some type of preference ranking and you rank those things. And then these rankings become the label. So when I train my reward model, this is my input and this is my label. So I'm actually training a regressive model which will produce this numerical output. So it's still a GPT, a large language model, it's just producing an output. All right, so then how do we train a reward model on AWS? Build and train one. So first, as always, I'm going to pop my data sets in S3, assuming I already have the labeled data, which I no doubt created using SageMaker Ground Truth. So I store my data sets in S3. Easy, done. I'm going to run a notebook, such as on SageMaker training, such as SageMaker notebook instances or Studio, to analyze my data. I'm going to develop my scripts, and then I'm going to run jobs for those things. And so again, I'll develop my training scripts from my notebooks, and then I'll run some training instances. And this is just to train the reward model. This is just to produce the reward model to give me a GPT-based model that, again, takes my text and returns the scalar output. So that's how to build and train a reward model on AWS. Now, I'm going to use my reward model to train a new LLM. So now I have this reward model, and I want to use this reward model to fine-tune this other LLM. So I'm going to do this in 2 stages. And the first is like my ahead of time pre-computing job. So ahead of time, I'm going to pre-compute my original model responses. So I'm going to run a CPU or a serverless job ahead of time. And this serverless job is going to go into my prompts data set. It's going to run those against my original pre-trained LLM, and then I'll just store my responses on Lustre. So the key here is that Lustre, my distributed training or my distributed file system, has both my prompts and the responses from my original LLM. From like my top LLM, my top foundation model, I'm storing both of those things. So I have both of those stored, and it might already be in my ranking data set. Like my ranking data set might just have this, so maybe it's easy. And so, yeah, so I'm going to run this whole thing and prep it and store it on my Lustre volume ahead of time. Then the fun part begins. Then I'm going to use what's called heterogeneous clusters. So heterogeneous clusters are a way in SageMaker to run different types of instance groups. So I can run instance groups with CPU and GPU. I can run GPU and Annapurna accelerators with Trainium, or I can run small GPU and large GPU. So in this case, I might run the G5 series with 4 GPUs to host my reward model. So again, because the reward model is smaller, I might have one small G5 instance type that is holding my reward model. And then, and remember, this thing is tiny. It's going to sit on just 4 GPUs. And then over here, I've got Big Bertha with all of my instances. And this is holding my massive LLM. So this is the 20 billion parameter model that I'm trying to fine tune using RLHF. So I've got my quite a few. I've got my 32 accelerators right here. And then here's how this process works. So for each step in this process, I'm going to go read my prompts and my responses from the original LLM. And I'm just going to read those from Lustre right here. And then the fun begins. So for each step, for the LLM that I'm fine-tuning, we're going to run the prompts through this LLM, and we compute the responses. So in our original syntax, that was like Y star. So we compute this Y star. So we take X and we compute Y star, and then we're going to send that to the reward model. So Y star goes to the reward model, which is sitting on these 4 accelerators over here, and I get this scalar reward signal. So I produce this reward signal. So that was that R theta. So I get this R theta. Then I'm going to run that KL divergence penalty function to compare those. So then here in step 3, I compare Y star that I got in point 1 with Y0 that I picked up over here. So I just compare these two. and then I add them together. So then in step 4, I take r theta, remember, which came out of the reward model, minus my epsilon times this penalty function, and then I use that to update my LLM. And I might add some gradients from the pre-training as they suggested in InstructGPT, or just pop this whole thing in my pre-training process, which to me seems like the more logical thing to do. So in any case, a couple pro tips here. I'm going to use smaller accelerators for the reward model because this thing is tiny. I'm going to use larger accelerators for the LLM that I'm fine-tuning. So larger accelerators and more of them because it's a bigger model. And then definitely when you keep all of them in the same cluster using heterogeneous clusters, your runtime is so much faster. If they're sitting on all different parts of the cloud, or if they're sitting in different regions or different accounts, or if they're not even in the cloud and you have to hop on another bandwidth, it's just going to be so expensive to train this model because you want the steps to be really fast. Otherwise, it'll be totally inefficient. So yeah, strongly recommend using heterogeneous clusters to use reinforcement learning to update your LLM.
All right, let's check out this demo. So you've heard about RLHF, you think it's cool, you've learned about heterogeneous clusters and all sorts of related topics. In this demo, we are going to do our best to implement this thing locally. RLHF, as you learned, is extremely complex, lots of moving pieces here. And let's try and break it down. So same as last time, actually we're in a new repo. This is the SageMaker Distributed Training Workshop repository. And you'll notice this is number 9 here, RLHF locally. Feel free to grab that QR code for the notebook. Alternatively, you're welcome to just use the short URL. All right, so I do indeed have this up, and let's see what we can make of this. So same as last time, I'm in a notebook. This is using SageMaker Studio. Major kudos to my friend EK here, Senior Applied Scientist at Amazon, for building this out. This thing is awesome. And so it's nice because this notebook is completely self-contained. So there aren't really many other files that you need in this notebook. Really everything is actually implemented in one notebook. So it's very, very tightly self-contained. And you'll find that it has a lot of PyTorch. There's an absolutely massive amount of custom PyTorch objects and custom PyTorch code that we're going to use to get this done. Now, I really want to see this type of technology become easier and become more simplified and more abstracted. So as time goes by, you builders out there, help me think through how to make this easier. It's really insanely complicated right now, and it's a bottleneck for a lot of people because many obviously believe that RLHF can give you a good model, but very few people have really state-of-the-art RLHF stacks. Like, I think that's probably the most important piece to the puzzle. But in any case, let's check this out. So we're going to install our requirements. Got a long list here for you of all the things that you want, including Xformers. We'll pip install that thing. Then we're going to go to our imports. These are all normal, TQDM, source typing, transformers, data collator with padding, apparently, and then the load data sets. And then lots and lots of PyTorch. And then we're going to define the model parameters. So these are the training configurations, the seed, 1024 sequence length, total number of epochs, steps, your batch size, things like this. I ran this on a G4.x. Yeah, so this has 1 GPU. It was still slow. It was a good 10-20 minutes just watching this baby run. So if you want to upgrade this thing, it'll run faster for you. CUDA, CPU, etc. Maybe that's why it's running so slowly. Because it wasn't even running on the GPU. That'll do it. All right. And then we're going to use Lewis's GPT-2, co-author of the book, Natural Language Processing with Transformers. And then we've got the Atom Optimizer, Weight Decay, Scheduler, this mysterious whitening method that I'm not sure what this is, PPO, and all sorts of other hyperparameters here. So anyway, we'll load those into this dict config, make them nicely accessible, and set the seeds. And again, remember, we're setting the seeds in the notebook because right now all of this is literally training on this G4. So now we have many PyTorch objects we're going to define. We have this prompt pipeline, and then that PPO RL element, this PPO RL batch, some rollout storage that includes a data loader. So your prompt pipeline has a tokenizer, and then we set the prompts, and then we set this input ID. Then we're going to use these decorators here and call this a PPO RL element. And then RL batch, this is taking the, this is setting the query tensor. And then this is setting the log probs, values, and rewards. And then we're setting, similar terms, but for a slightly different object. Then we have this PPO rollout storage. I wasn't exaggerating, it's a lot of PyTorch. We're going to create this loader, inside of which we are defining another function, oh joy, and we'll return it. And then we have yet more PyTorch functions to define. So there's this whiten process, GAE, takes the values and rewards. Then we have this PPO loss, it takes the values, loss 1, loss 2, then the delta. Ratio, and that is your net loss. And then the loss function, which invokes that, model.device, query tensors, response tensors. All right. And then the PPO loss that takes all these things and then returns it out. And then your actor, which operates at a slightly higher level, takes the prompts, eats them in chunks, and then we make this experience. I'm so glad EK wrote this thing. Glad, because it would take me a lot longer to do that. Alright, generate, get model inputs, log probs, goodness gracious, agent, generate, transformer outputs, and so on. Alright, so now we have all of those very verbose things defined. Now we're going to define the pipeline that invokes those things and uses them. So this is going to use a Distilabert IMDb, still from Lewis. We're going to load it through the load dataset function. So we got the IMDb with our train test splits. Pick out the prompts from those. Get your tokenizer. Download the prompt pipeline. Then we're going to load the model. So let's just see what this model is here. So the model path, which points to that model we downloaded above. And then we have this config, number of layers unfrozen, and that we set to the device. So those are the trainable layers. Sounds about right. Tokenizer. We generate the output IDs. Okay, so here's the before. Essentially, we're taking some of the prompts, and then we're going to send those prompts to the model, And the model's generating movie reviews, actually, just to use some basic data. So it's generating movie reviews, and then we're going to put this into a reward function. So the reward function takes the generated text, which here is these 3 sentences. So this is the first review, and then this is your second review, and then this is the third one. And the goal here, so imagine that this is the response coming out of the GPT model that you want to fine-tune or you want to update and optimize. Like, the responses are okay, but they're not that good. And so you want to use your reward modeling stack to make them better. This is how we're going to do that. So first we need a way of saying how good and how bad these reviews are. And that's what the reward function does. Actually, in this notebook right now, it's not even training a reward model. It's just returning these scalars. So we're still working on the reward model training. But in any case, it takes this generated text, 1, 2, 3, and then it generates or it outputs this number. Higher is better. And so this is basically saying how confident the model is that this really is a legitimate movie review. And so it feels very confident in the first one, and notably not just being a real movie review, but being a positive review, actually. So in this first one, clearly positive. Second one, clearly not positive. And then the third one is positive as well. All right. So now that we have that, we're going to put this into an overall training loop, and then we're going to run this loop. So it takes the prompt pipeline, which is this. It takes an actor, which we built earlier. So the actor takes the prompt pipeline, actually. The actor takes a tokenizer, and then your chunk size. And then the storage here in the PPO rollout storage. We have this Atom Optimizer, then a scheduler, and then the updates per batch. And so we're going to take 400 steps, and then here's our training loop. So we're walking through the number of epochs, and then essentially for each point in the number of epochs, the actor makes an experience. And so in RL, that means the actor takes an action, basically. And then should gets a reward from that action. We're going to try and replicate that. So the actor makes some sort of experience, which creates this rollouts concept, and then stores that in the history. So this is how the PPO process tracks where the actor is in the environment, is with the store. So store.clear history, and then store.push, which takes the rollouts. And then actually here we create the data loader. So then based on the, so we create this data loader, evidently, and then we're going to walk through the data loader. And for each of those, we'll take a step. And so for taking those steps, we get this batch. We pass the batch through this loss function, which is going to invoke the model, which returns this loss and the reward. And then we say loss.backward. We take a step on the optimizer, zero out the gradients, take a step on the scheduler, and then update this description. And so this runs all the way through. It takes 400 steps, hits 100%. And then in the last part, we're going to use this updated LLM to generate new text, and then we're going to evaluate that with the reward model. And so our tokenizer takes, actually these were the same 3 prompts. So my feeling about the movie, prompt 1, this is prompt 2, and I can tell with certainty, prompt 3. So we take the same 3 prompts, tokenize those things, pop them into the model, generate the text, run that back through the tokenizer, and then once it's back in natural language, we put that into the reward function, and then we get this part. So this is the full review with a 98%, and then the second one, 99%, the third one, 98%. So much higher than we saw previously, and that is because of this very strong reward signal. So remember, the model is just really optimizing for this reward signal. And then on top of it, we have the RLHF process sort of tracking the difference between the text that's generated from the model we're fine-tuning with the original model to mitigate the reward hacking too aggressively. So you still have some reward hacking, which is good, but mostly you want sort of quality learning. All right, so that's RLHF in a notebook. And actually, I mentioned on the GitHub that, again, this is sort of insanely complicated, and so we're working on basically other examples just here in the GitHub to make this easier for you. And so that's going to be in the work in progress, little directory, containerizing this, simplifying it, making it easier for you to poke at things and generally train your models. And so with that, I hope you enjoyed this video. In the next one, we're going to learn how to deploy large models on AWS and on SageMaker. So hope you enjoyed this. And again, EK, massive shout out. Thank you for this awesome notebook. It's truly a labor of love. So thanks, folks. See you next time.